Looking at the views and how well the videos are performing, I have decided to abandon the solutions of the previous section. Instead, let us start the next section. This one is on Hermitian unitary and normal transformations. We are going to use two facts in this section without proof. The first one is this: all roots of a polynomial f of x coming from this ring. What is this ring? This is the ring of all polynomials over the field of complex numbers. That means here we are having those polynomials which have all their coefficients complex numbers. For any such polynomial, all its roots are again inside C. To put it more simply, if you take a polynomial whose coefficients are complex numbers, then all its roots are also complex numbers. This fact has a name. It's called the fundamental theorem of algebra. You may have already come across this. This is one thing, and this is fact 2. The only irreducible non-constant polynomials in this polynomial ring of real polynomials are those of degree 1 and 2. It can be shown that these two facts are equivalent to each other. And there is one more convention that we are going to adopt for this section, that all our vector spaces will be finite dimensional inner product spaces over the field of complex numbers. Occasionally, they will be over the field of real numbers unless stated otherwise. And today we are going to see this lemma 610(1). Let V, as I said just now, let V be a finite dimensional inner product space over the field of complex numbers. So there is an inner product on V, and let T be a linear operator on V. That means T is coming from this operator algebra A of V, which consists of all linear operators from V into itself, such that the this is inner product. You recall that when we discussed inner product previously, we used this notation. The inner product of the image of V under T, Vt, that is one vector, and V is 0 for all vectors V in V. If so, then the operator T is just the 0 operator. Let's now prove it. So the proof starts like this, by taking any two vectors u and w in V, and for such vectors we consider this fact. This is given to us that the inner product of Vt and V is equal to 0 for any V. So in place of V we can consider u plus w. Then also this will be true. The T image of u plus w and u plus w are orthogonal. That is, their inner product is 0. Because T respects vector addition, so u plus wt is ut plus wt. Alright, so that's the next step. And then you expand this inner product using linearity properties of inner products. So that way you get ut comma u plus ut comma w plus wt comma u plus wt comma w. Now again you use this fact here. This will be 0, and similarly this will also be 0, leaving us with this ut comma w plus wt comma u equal to 0. Note that this thing is true for any u and w, and now we are going to use this fact. Now using the fact that here w is arbitrary, we replace w with iw in this equation, and still it will be true. And do not forget that our underlying field of scalars is the field of complex numbers, so we have I available to us. So if you write iw in place of w, this is what you are getting: ut comma iw plus the T image of iw comma u equal to 0. Now due to linearity, or rather I should say conjugate linearity, if you have a scalar here in the second component of the inner product, you can take it outside, but it does not come out as it is. Actually its complex conjugate comes out. That is why you have minus I here, because the complex conjugate of I is minus I times ut comma w. And here we have to write one more step before we can take anything outside. So you have here I times the t image of w. Why? Because t is a linear transformation, so t respects scalar multiplication, and then in the next line you can take this I outside, because this I is multiplied with this vector in the first component. So I this time just simply comes out as it is by one of the properties of inner product, and then after cancelling I from both sides you get another such equation, which is almost like this one, but the only difference is that here you have a minus sign. And now we are going to add these two equations. So we write like this, adding the two equations in boxes, this is what we get, because if you add, then this one and this one cancel out and you are left with 2 times the inner product of wt and u, that is equal to 0. So this inner product is equal to 0. Note that you have found the fact that this inner product is 0, and this is true for any w and any u, that any aspect is still with us, and now we are again going to use it. So we write in particular the inner product of wt with itself is also 0, because in place of this u, you can take anything, so you can take wt as well. But you know that when a vector is having 0 inner product with itself, that can only happen when the vector itself is 0. But now you again use the fact that w is any vector in our vector space. Applying t on that gives us 0. So by definition t is the 0 operator. So here the proof ends.